All right, so let's talk about parabolas. And as always, we're just going to start about what's the definition of a parabola. So the definition of a parabola is the collection of all points in the plane that are the same distance from a fixed point, we'll call this fixed point the focus, F, and a line, the directrix, which is we're going to call capital D, the directrix. So what does this look like? I'm going to deliberately draw this thing kind of sideways, but let's sort of draw a parabola. Get yourself a nice little parabola here. And parabolas, they're not pointed at the bottom; they're nice and smooth, kind of U-shaped, right? And just open up. And there's an axis of symmetry that goes up right through the middle of them. And so let's take a look at this. Let's put right here. Let's put our focus in capital F. And then, okay, so it says collection of all points in the plane that are the same distance from that focus and the directrix line. So I'm just going to go ahead and put this directrix line right here. I'm going to label it capital D. So now let's look at what it means to be a point on a parabola. So look at this red point right here. Okay, so what's the distance here? The distance to the focus in red here. And remember, this is not to scale, so this may not be perfect, but this gets us the idea, is going to be the same as the closest distance of that point to the line. So the closest distance from a point to a line is going to be going straight to a perpendicular line. Like we wouldn't draw this as the distance from that point to the line D, but rather just drop that line straight down in the perpendicular manner. So this is equal to that length. The distance take a point on the parabola, you've got equal distance to the focus and a line. So here's another point on the parabola, and so the distance over here is a little bit shorter, but then also the distance to the line dropping down that right angle line. Sure enough, these two lines have equal length as well. And that's really what it means to be a parabola. So if I were going to label these things, I could label this red point P, and point P would have the same distance to the focus F and the line D, same distance. So we're used to seeing parabolas as being y equals x squared, right? We studied them a lot, y equals x squared. That was a whole lot in college algebra and previous maths up until now. But we can do them sideways as well. There's nothing stopping us to taking x equals y squared. And then we would have that. Well, there is something stopping this. It's not a function, but it still may have some useful purposes here. And so that's why I drew it kind of diagonally. It doesn't have to be straight up and down. We're not going to get into diagonal parabolas per se, well, too much, at least right now. But I do want to emphasize it could be both x or y direction. So let's take a look at the next two slides. Let's kind of just give ourselves kind of an intuition of parabola and what it looks like. Kind of focusing on that definition of collection of points that are the same distance from the point on the graph to the focus and to the directrix line. So let's have a quick look at this demo calculator here. And as we kind of zoom, well, I don't need to zoom in here, but that red distance is the same as that blue distance. And as we kind of move this point around, hopefully you can kind of intuitively see that those two lines sure look like they have about the same length. And that's really the intuition here. I made this graph, and so it's flawed. It only goes to there. Like you can't go to the other side of the parabola. Just wanted a quick look at that. Okay, so back to our slides. Okay, so we're gonna really attack this thing. So here's our picture, and you know what? We're gonna label this point here. Any point on this parabola, this arbitrary black point here, I'm gonna enable it point, and I'm gonna call it x comma y. Just arbitrary point. It's got an x and a y coordinate. Okay, so things I haven't told you yet. So we've given the focus a point a name of 0 comma p, that f kind of there. So what about this directrix line here? Well, I'm going to tell you now that this is a horizontal line, so it's y equals, and since her parabola has its vertex at 0, 0 at the origin, the focus tells us that this has a distance of p. Well, definition of parabola says that the origin, the vertex of this parabola, should have the same distance to that directrix line below. And so this distance must also be p. And so the equation of this line is going to be y is equal to negative p, because we've gone down p from 0, whereas we went up to get to the focus. So let's see, the distance from the focus to the point on the parabola is that blue distance, and that's the same as this red distance, which is the distance from the point on the parabola to this point down here on my directrix line, which I'm going to call this point capital Q. You know what? Let's put that over there. Capital Q equals, well, what is Q? Well, Q shares the same x coordinate as the point P above, so it's going to be x, comma, but its y coordinate is on that horizontal line, so it's negative P, so it's got a different y coordinate. So let's see. This blue line we could label as line segment FP, and this red line we could label as line segment PQ. We're really going to kind of get crazy here, and we're really going to dive deep on this idea that these two, the definition of a parabola, that these two lines have the same distance. So let's look at that. Okay, so distance, and we're going to pull back on some old math here. The distance formula between 2 points is really just an application of the Pythagorean theorem, and I encourage you to draw the picture and kind of figure that one out. But really what we're interested in here is the distance for FP is equal to the distance for segment PQ. PQ here. Okay, so let's look a little bit carefully at what is the distance of FP. Well, FP is going from the point 0, comma P, that's F, to the point X, comma Y. So the distance formula is the square root of x minus x squared and y minus y squared. It's really just an application of the Pythagorean theorem, as so many things are. So x minus x is going to be x minus 0 squared plus y minus y coordinate squared. So y for this y minus the other y coordinate, so y minus p squared. Okay, so there's our distance for our line segment FP. What's the distance for line segment PQ? Well, PQ goes from point XYP and connects it to point Q, which is x comma negative P. So our distance formula here is going to be subtract the x coordinates, x minus x, square them, plus subtract the y coordinates, y minus a negative P quantity squared. Okay, so there's our formula for PQ, the distance of PQ. If you wanted to get fancy, we could recall that we learned about magnitude and sort of put some double bars here, but that's just getting silly now. Okay, back to the task at hand. Let's simplify this whole expression. So this left side becomes x squared plus quantity y minus p squared, all underneath a square root, is equal to, and on the right we get 0. X minus x is 0, so we are just left with that's 0. So we're left with y plus p quantity squared. Okay, so that's fairly nice. And we're just playing with stuff. We're seeing where it goes. We're going to try and come up with a generic formula here. Okay, so what do we got now? So I don't like the square roots, so we're going to square both sides. And that means we're going to get just what's underneath the root. X squared plus y minus p quantity squared equals y plus p quantity squared. And we've dealt with those roots. So now let's just sort of dive in on this and do some algebra here. I'm going to run out of room here, so I'm going to preemptively take this and transfer it over here to give me some room. Okay, so x squared plus y minus p times y minus p is equal to y plus p times y plus p. And multiplying these out, we are going to get x squared plus y squared minus yp gives me 2yp plus negative p times negative p gives me positive p squared equals, now I'll multiply this out, we get y times y gives me y squared, and plus yp gives me 2 of those plus 2 yp's, and then p times p gives me plus p squared. So what can we do now? Well, let's see what color. I'm going to use green here because green hasn't been serving a purpose. Now I'm just going to kind of move things around. sort of stick things on the same side and see what happens. Well, I see that I got p squared and p squared over here, so you could think of that as, well, I can subtract one that's going to go away, and I see a y squared and a y squared. But let's move things from the left to the right. So we'll subtract y squared over here, minus y squared. That'll give us 0 on both sides, minus p squared, minus p squared. Again, that tidies up to 0. That's gotten messy, so let's rewrite it. X squared minus 2yp, I'll leave a little room, equals 2yp. Interesting. Okay, so what do we want to do? I feel like I'm going to try and get this x squared by itself and put all the y guys on the other side. So we're going to add 2yp to both sides. That'll add to 0 plus 2yp. That will give me x squared equals 2yp. I mean, not 2yp. 2yp plus 2yp gives me 4yp. And so what do we have? We have this generic little formula here. Well, we're used to parabolas being y equals something. So let's kind of take this guy and solve it for y. Okay, so we got x squared equals 4yp. We could divide both sides by 4p, and those would reduce away. Whatever you do to one side, you got to do to the other side. So you've got y is equal to x squared over 4p. So y is equal to 1 over 4p times x squared. There's kind of a nice formula for a parabola. And this p value is the distance from the vertex to the focus and the distance from the vertex to the directrix. So you've kind of defined both of the points that are important about a parabola. So there's kind of two main forms you're going to see this guy written. It's the one I just circled, and then it's the one we started with to get there. X squared equals 4yp as well. They're the same. And we could play this same game for a sideways parabola, so to speak, opening left or right as well. Only then it's going to be y squared equals 4px. 4px. And yeah. So let's do another, kind of just keep this idea going. And let's just take a look at things in general. So in general, we'll draw ourselves a quick picture of a parabola, not on any xy axis here, just an arbitrary picture of a parabola. And we know parabolas have an axis of symmetry. Well, let's label that. Let's call this the axis of symmetry. And then we've got our vertex here, and our vertex, as usual, we're going to express in terms of h for the x coordinate and k for the y coordinate. And we're going to have a focus on that axis of symmetry, or focus here, and that focus is going to be this distance p. So the focus actually has coordinates, and I'm going to run out of room here, so I'm going to write it over here. The focus has the x coordinate is on that same x value as the center, so h, but the y coordinate changes. The y coordinate goes up, so you have k plus p. Now that directrix line below this, a lot of similar logic here. It shares the same distance from the point on the graph, the vertex, so it's down p units. And so this directrix is going to be y equals k minus p, because you started at the y value and we went down at that p value. So it shifts down your vertex by p. And you could really play this same game with all of the other direction, possibilities for orientations of a parabola. You could have it opening to the right. You could have it opening to the left with a vertex and a focus and a directrix. Or we've done one for opening up already, and so we'll draw one that looks like it's opening down. So you got your directrix and you got your parabola and your focus there. So this kind of been an introduction to the just general anatomy and like definition of a parabola. It's all defined by that p value. If you know the vertex, find that p up to the focus, down to the directrix.